All right, I hear the bell, so why don't we get started? So 欢迎大家参加，今天是这个我们这一次ACU Delta 讲座的第二个演讲啊。昨天这次的得奖者是德州大学 Austin 的那个 Professor Stella Offner， 我们帮他取了一个中文的名字了，这个欧偲辰，欧当然就是他的姓啊，那偲就是他的名字，然后辰就是星星啊，他的名字就是恒星嘛啊，所以那欧偲辰教授那个很高兴也展现了 Delta 的影响力啊，他们的美国的代表呢就飞到Austin 去亲自颁奖，那现在荧幕上就是他们的代表颁奖给这个 Professor Offner 啊。那昨天那个 Delta 讲座一直是我们已经办了大概十几年了啊，那就大概每一年有1个到2个年轻的天文学家，我们认为他具有学术影响力，将来会有潜力会是学术领导者，那就请他们来台湾演讲，然后跟当地的学界跟学生互动。那这2年当然因为疫情的关系呢，就没有办法亲自来，然后我们也一直推迟，因为想说怎么样能够等疫情过去啊。所以这一次的讲座其实是Professor Offner 欧教授的，其实是我们2021年的得主啊，那一直延到现在呢才演讲。那昨天欧教授已经给了我们一场学术的讲座，有关于恒星形成利用机器学习等等啊，蛮精彩的。那今天呢是Outreach Talk， 是希望是针对比较科普的这样子的。那他讲的讲题是双星，天上的星星多半都是双星可是我们太阳不是。那我们来听听看，怎么样这个对于双星的最新的研究，他们怎么形成的？有哪些种类，以及它们对于行星的形成又有什么样的影响？ So Professor Offner is going to tell us about stellar multiplicity, their formation, and implication on planet formation. 那在这个过程当中我的建议是，你如果有问题就请你打在这个那个讯息栏那边，不要用声音打断，我们等到后来呢再用声音来提问题。那至于你打的 message， 你用中文英文都可以，没有关系，用问的时候呢也可以用中文英文，都没有关系，只要我们听得懂了，我们就试着翻译一下。那Offner 教授很棒，他把一些重要的字都用中文标示了，所以我相信可能要打断的机会不多。以前的科普演讲，我就是隔一段时间，比如说4-5个投影片啊，我觉得需要补充一些基本的资料的话，我就会稍微讲解一下。我预计今天这样的机会可能不多，不过如果有需要的话，或者是你可以 voice， 你可以写在你的那个 message 说哪边要再讲清楚一点的话，那样子还是可以打断的啊。All right, so I will hand the time to you, Stella. So let's start.
All right.
I'm sorry. There's still I'm sorry. There's a video clip from Bruce Chen. I forgot about that. I'm sorry. All right. So let's have that.
Good afternoon, Professor Stella Offner, and all attendants of this lecture. I'm Bruce Chen, the founder of Delta Group. Today I'm very glad to see this astronomy lecture being held successfully. I want to thank the National Central University for hosting the event with us. As most people know, I'm an astronomy enthusiast. This is why I formed the Delta Young Astronomers Award. more than 10 years ago. This award recognizes young scholars who have made remarkable contributions in the field of astronomy. Through this award, I hope to foster more interaction between amateur and professional astronomers. I also want to make the latest studies being popularized in Taiwan. These 2 years, although the pandemic disrupt people travel, the meeting opportunities, it won't stop as an astronomy enthusiast like me exploring the knowledge about our starry sky. I'm very happy that this year Professor Offner became our outstanding awardee. She is currently working in the University of Texas at Austin and particularly focused on star formation, molecular cloud properties, and evolution. It's definitely our pleasure to have her with us to speak on this topic. Now I need to stop here and yield the time to Professor Offner. I believe the lecture will be very interesting and hope all attendees will learn something new today. Thank you.
All right. Thank you. All right. So now you can start. Sorry about that.
All right. Thank you for that introduction. And I want to say it's a pleasure to be here with you today, talking about a topic that is near and dear to my heart, which is stellar siblings. So first, I want to give some motivation of the big picture of what I do. So I use large-scale simulations to model how stars like our sun form. And though we've been staring at our sun for all of our history on this planet, there are still so many things that we don't know about it. We don't know, for example, why there's only one sun in our solar system. We don't know why our sun has the mass and size that it does. And we don't know how our planets formed and what set their properties. And so these are all areas of inquiry. And this particular lecture, I'm going to talk to you about how our sun formed and why it does not have a stellar sibling. And we're going to start by talking about star formation in the galaxy. All right, so first I'll give some examples of multiple star systems and discuss how stars form and how multiples might form differently than stars like our sun, single stars. And then I'll present some observational challenges that astronomers have in studying these systems and some recent discoveries that we've made over the last decade. And finally, I will discuss what all of this means for planets and planets around other stars. So our sun is lonely. What I mean by that is space is just vast and very empty. So that if our sun were only 43 centimeters across, the next closest star would be on the other side of the Earth. So space is filled with emptiness. Now, many stars are not lonely because they have siblings. So for example, a star might have a companion. So there are two stars in the system. So we call those binary star systems. One example of this is Sirius AB. This is an image of this binary star, and they're actually so close together that you need a high resolution telescope to observe them. But it turns out that Sirius is actually one of the brightest stars. It's the brightest star in the night sky. So you've probably seen it if you looked up into the sky. So it and its companion are only about 20 astronomical units apart. So an AU is the distance between the Earth and the Sun. All right, so this star is 20 times further away from its host star than our Earth is from our Sun. So if you want to go and try to find this binary, you can start by looking for the Orion constellation, which has a belt of stars as its signature. And then you follow the line of that belt down, and you see a very, very bright star, and that is Sirius. But looking with your naked eye, you will only see what looks like one star. All right, so the most famous binary system is, of course, this one from Star Wars, the Tatooine system. And maybe you have been seeing this system a lot if you've been watching The Mandalorian and Boba Fett like I have. But this particular system has a planet that orbits two stars, a binary system. All right, so many stars have siblings, and some stars have three stars within the system. We call that a triple star system. So one example of this is Alpha Centauri. Alpha Centauri has two more sun-like stars that are very close together, and a third star, Alpha Centauri C, shown by the circle, that is much smaller and much further away. So if you were to look for this system, you could find it by first finding the Southern Cross, this cross of stars, and then looking a little bit over to see a very bright star. So this Alpha Centauri is actually the closest star system to our own. So if we were going to go and visit the stars outside of our system, go and visit potentially other planets, this is the first place we would go. So this is the most famous triple system, the Tri-Solaris system in the three-body problem. I don't know how many of you read science fiction, but this is a really excellent book where the whole premise is about multi-star systems. In this particular case, there are three sun-like stars that are on chaotic orbits. So these suns are continually changing their position with respect to one another. All right, so most stars have siblings. Finally, there are four star systems, which we call quadruple systems. So one example of this is Mizar. So Mizar was initially one of the first, what we thought, binary stars that we saw with a telescope. But in the late 90s, we realized that each of those binary stars also had a companion. So if you want to look at Mizar, you can find it by finding the Big Dipper, and it is the second star within that constellation. So how special is our sun? How many other stars out there have companions where our sun does not? So this is a plot showing the fraction of star systems that have two or more stars. So we get this number just by going out and counting the number of systems with two stars, number three, number with four. We take the ratio to the total number of systems that we see. So here is our sun at one solar mass, and the bottom axis has primary mass, which means the largest star mass in the system. So if we draw the line up, we see that about half of stars like our sun have at least one smaller companion. Now, sun-like stars might also be companions to more massive stars, which means that more than half of stars like our sun are actually in systems with a sibling. We can also look at the triple fraction. So this is the fraction of systems that have 3 or more stars. So if we find our sun here on the x-axis and follow it over, we see that about 10% of stars like our sun have 2 smaller companions. So triple systems are fairly rare, but binary systems are quite common. So how do 2 stars end up close together? So the answer is they were born that way, right? They are truly siblings. So unlike siblings, unfortunately, stars can actually be much larger in comparison to each other. So often you can have very different sizes between these 2 stars. So astronomers have studied that distribution to measure the masses of these multi-star systems. So here's a plot showing the ratio of the mass of the little star in the system to the biggest star in the system. So here's our sun on the x-axis at 1.0. And if you look at the other axis on the y-axis, you can see that there is a line in which stars are equal mass. So we do call these stars twins because they are the same type of star in the same system. So if we look at our sun here and stars around its mass, you can see that there's a huge range of ratios. So a star like our sun might live in a system with a star that has a very similar mass and size, or it might live in a system that has a star 10 times less massive. So there's a really big size difference between many star binaries that are out there. So another question you might want to know is, for these type of stars, how far apart are they? So astronomers have also studied this distribution, and they measure the typical separation between the 2 stars. So that is sort of the average distance. For sun-like stars, that's this black and yellow curve. And you can see that the peak of that distribution is about 50 AU. As you go to much more massive stars, they tend to be maybe further apart. If you go to very low mass stars, 1/10 of the mass of our sun, they are much closer together. So for reference, the average distance between the sun and Pluto is about 40 AU. So in these typical multiple systems, these stars are about as far apart often as the sun and the gas giants, the sun in the outer Kuiper belt. Yes, Wenpin.
好，这边我稍微解释一下，我们常常挂在嘴巴上讲说，天上的星星多半都是双星啊。那这个比例是不容易叙述，因为你可以问说，天上你指一颗星，它是双星的几率是多高？或者你可以问说，因为在双星里面是2颗星嘛啊，你也可以问说，宇宙里面这些星星呢，它在双星系统里面的比例又是多少？这2个数字是不一样的啊，所以刚才花了一点点时间在讲说它的定义，就是说是有一个比例啊，是双星、3星这样加在一起。那双星有一些特殊的参数，第一个就是质量比，所以上一张投影片就是讲质量比。那后来的一张投影片，这一张就在讲分离距，他们的轨道的距离。那得到的结论，我想中文都写得很清楚了，就是一般大概就是50个 AU， 就是我们差不多我们太阳系的行星系统这么大了啊。那但是不同质量的星球呢，它又有不同的参数。All right, back to you.
All right, thank you. Okay, so now that we know that these stars are born like that, the question is, how do we actually form stars? So I'm going to break the problem up into a set of different gas densities, starting by journeying out beyond our star system to where space is very empty. So here I'm going to count the gas density as the number of atoms per volume. So for example, 1 would be 1 atom per centimeter cubed. Yes, Wenping. Is your hand still raised from before?
Probably. I'm sorry.
Okay. All right. Okay, so let's go out beyond the edge of the solar system. Now, if we go out there and we count the number of atoms, we find that in 1 cubic centimeter, there's only 1 atom. So it is very, very low density. So luckily, stars don't form out of interstellar gas. Instead, they form out of giant clouds of gas. So we call these giant molecular clouds because they're made mostly of molecular hydrogen. So that gives us 2 orders of magnitude where these clouds have an average density of about 100 particles per centimeter cubed. Now, one of those clouds would form something like thousands of star systems, and an individual star, like our sun, would have formed out of a prestellar or dense core. These have densities of 10 to the power 4 or 5, so 10,000 to 100,000 atoms per centimeter cubed. So moving up, we finally get to the lowest vacuum that we achieve in the lab here on Earth. So this is about 1 million atoms per centimeter cubed. So this explains why star formation is not a laboratory problem. We can't go into the lab and model the conditions that go on to make stars. They're just too extreme. All right, so moving up, we get to these old school light bulbs, which are actually evacuated around the filament. And they have 10 to the power 15 atoms per centimeter cubed. Here's the air, like we're breathing, 10 to the power 20. Here's you, about 10 to the power 24. And here finally is the center of the sun or a star, 10 to the power 26. So along this number line, we pass through something like 20 orders of magnitude, all right? This is an extreme range of conditions through in order to make a star. So how does that actually happen? What goes on? And the answer is that this is primarily due to gravity. So once a certain density is reached within these giant molecular clouds, the atoms attract one another and begin to collapse under its own gravity. So we call this process gravitational instability. It's a runaway process. So once it gets started, it collapses faster and faster, and the gas gets denser and denser. So you haven't heard about gravitational instability as a catastrophic event here on Earth. You've heard of tornadoes and earthquakes, but you haven't heard of this gravitational instability because we can only get those kind of conditions in space. So if we take the air in the room, the amount of mass that you would need would be about 10 times the size of the Earth. So there's no way we could get these kind of conditions here on Earth. However, this happens quite a lot in the gas in space, in these clouds, and this is what is causing the stars to form. So because star formation is not a laboratory science, we use another tool to study it. We use numerical simulations, which is what I do in my work. So we basically use computers to solve the equations to describe the gas behavior. So here's an example. This is showing you, it's a 3D movie showing you gas density. We're zooming in, and time is going to start going forward now. You can see the gas is collapsing and moving to higher densities, and we see 2 stars are forming, and we're zooming down into 1. You see this star has a flattened structure, which is an accretion disk. So let's look at that a little bit more carefully. So here's another movie showing this process. You can see the gas is funneling down towards the star. You have this flattened disk, and there's a spiral structure that's happening around in that disk. And that is one of the signatures of gravitational instability. So this process is really about angular momentum. It is angular momentum, conservation of angular momentum that forms this disk. So what happens is as the gas goes from large to small scales, the angular momentum is preserved. So this is exactly like an ice skater. As they bring their legs in, they spin faster and faster. And when this happens to this gas circling around the star, it creates a flattened disk structure. So it is this disk structure that is ultimately where planets go on to form. All right, so how do we form multiples? There are 3 different ways that this can happen. So first, you can have disk fragmentation. So this is where this accretion disk around the star has so much mass that gravitational instability happens again and produces a second star close to the first one. So here's a simulation of that happening. This is a high mass star formation calculation. You can see the flattened disk forming in the bottom, spiral arms, and then you can see a number of secondary stars form within the spiral arms, and now you see 2 binaries orbiting one another. So it turns out that massive stars that are 10 times the mass of our sun, are much more likely to experience this type of disk fragmentation. And so, as we saw before, their multiplicity fraction and triple fraction are quite high. Wenping?
好，我打断一下，刚才那个有关于这个20个数量级的那个我觉得是非常棒的一个展示了啊，就告诉我们说，恒星形成或者在太空里面的这些环境啊，在实验室里面现在还制造不出来那样子的真空。那即使是做电脑模拟啊，那在这么大的这个变化密度变化这么大的情况之下，也都是很具挑战的。那我们今天听到的演讲当然是就是做数值模拟，我们把适当的我们知道的物理丢进去，然后让电脑去跑，看看出现什么样的情形。那刚刚解释了一下恒星怎么样形成，达到了一个临界的密度以后，一个东西就会靠自己的引力收缩下去。那在地球上没有这样子的引力造成的，因为我们的那个不够大啊，或者是说我们在这么小的空间里面不够密。那讲完了以后，恒星形成，现在就要讲说双星的形成，多星系统的形成。那第一种可能是因为当时缩下去的时候，角动量要守恒，它就会变成一个盘状的结构，那个叫环星盘。那环星盘还在吸积东西，要让恒星长大，所以那个也叫吸积盘。那第一种可能就是吸积盘本身分裂了以后呢，那就会制造双星啊。那这张投影片听到的地方就是说，是大质量的恒星比较有可能是有这样子的形成的机制。All right, back to you.
All right, great. All right, so the second way to form a multiple star system is through core fragmentation. And this is this dense gas that is forming the star, but it is not spherical like we saw in the other picture. Instead, there can be structure within it, which leads to gravitational instability happening more than once on these scales. So for example, like this, from a simulation, forms 3 stars within the same dense core. The last way to form multiples is something called capture. This is where stars might form in two separate dense cores, but their motion brings them together and they become gravitationally bound. So this movie will show that process. You'll see a second star coming off from the side and joining with this first star. So there it comes. There's actually two there coming and joining. This is looping, so you can see it happening multiple times. So this is an example where we have core fragmentation. You can see the second two forming, and then capture, where they come and join that other first star to form a triple system. So what we know is that neither disk fragmentation, core fragmentation, or capture happened in our solar system. We know that because there's only one star. So what we want to know is how common are these processes in nature? So that leads me to observational challenges. Can we actually see this in action? So it has been very challenging to study how stars form with observations. One reason is that the gas density in these molecular clouds is very high. Now it's very low density compared to the air, the densities that you are used to, but for space, these are very high densities. So there is a lot of material for the light to pass through in order for us to observe what is happening. The other problem is that the stars are very far away. Their star-forming regions are a few hundred light years away, meaning it takes that light a few hundred years to get to us. And because they are so far away, we can't observe what's going on in very small scales. Recently, we've had some amazing developments with a type of telescope called an interferometer. The most well-known example of this is the Atacama Large Millimeter Submillimeter Array. And we say it's an array because it's made up of an array of dishes, so a bunch of small telescopes, in this case 66 total. And what we do is we combine the signal from all of these different dishes to make one image. And this allows us to get much better resolution than we otherwise would do. And just to say, this telescope is observing in radio waves, so very long wavelength light. Wenping?
好，我稍微这边讲一下，因为这个蛮重要，因为我们台湾中研院有参加这个 ALMA 这个计划啊，它放在智利，那因为它叫干涉仪，各位可以看到照片上，它是由不同的天线，然后它们各自接收讯号，看同一个天体，然后把他们的收到的讯号呢彼此处理，彼此做干涉，就可以得到虽然各自加在一起的面积啊，收到的讯号还是加起来这么多，可是因为它分开来，隔着很远的距离，从不同的角度来看同一个天体，所以它就可以得到比较好的解析力啊，所以 ALMA 干涉仪呢是目前在电波波段、次毫米、毫米波段观测恒星形成最有威力的一个工具。Thank you.
All right, thank you. The last problem is that there are very long time scales involved in star formation. So a cluster of stars might take millions of years to form. An individual star might take up to 1 million. That's the time to accrete all of its gas. So we can't observe stars forming in real time. So when we look out in the galaxy and we see star-forming regions like this one, 30 Doradus, we only get a snapshot. We only get one picture. So numerical simulations can help us fill in this gap. So despite those challenges, we've made a number of discoveries over the last decade. in particular thanks to these interferometers like ALMA. So in 2015, we were able to capture for the first time a forming quadruple star system. So we zoomed in on this region with higher resolution, and we found that there were 3 gas blobs here, which were almost ready to form a star, and 1 already formed young star, a protostar. And all of these were gravitationally bound together, so that when the gas finishes collapsing and forming stars, this would be a 4-star system. The next year, we had another discovery, this time a triple star system. In this case, it was within a disk. So here you see the spiral structure of a disk, and there are 3 bright blobs here. Each of these is a young protostar that's continuing to accrete gas. So the last example was core fragmentation. This one is disk fragmentation. So here's an example from a simulation. You can see an unstable disk with 3 young stars in it. Last, an example of formation by capture. So what happens in these systems is that as these stars are moving together and pass by, they interact, and you can have this long tail of gas called a tidal tail that results from that interaction. So this was observed with ALMA in 2018. And here's a simulation example where you can see that these 2 young stars and their disks are connected by a stream of gas. So what is the implication for other planetary systems? So given what we know about how these multiple star systems form, what does that tell us about what planets might be like in these systems? So going back to Tatooine, this is a circumbinary star system. So we'll define that in a second. So it turns out that these type of planets in binary and triple star systems are not science fiction anymore. So here's an advertising poster. If you want to travel to another star where there's a second star within the system, you can relax on Kepler 16b, where your shadow always has company. So this is a real planet around a real binary star system. So the Kepler mission has revolutionized our picture of planets in these types of systems. So the way Kepler works is it observed a patch of a sky, and it looks for changes in the light coming from the stars. So as a planet passes in front of the star, there's a dip in the light coming from that star. So as it's passing, it blocks some of the star light in a very characteristic pattern, which is recorded by this telescope. So Kepler was able to observe for a number of years, and so it caught a very large number of these transits of planets passing in front of stars. So here is a distribution of these planets found by Kepler. The x-axis is the orbital period, so how long it takes that planet to go around the star. So our Earth's orbital period is 365 days. The y-axis is the size relative to Earth, right? So Earth is 1 on this scale. Neptune is about 4, and Jupiter is more than 10. So this is Earth radii. And you can see that Kepler has found more than 1,000, by last count, planets around other stars, usually with orbital periods of a few to maybe 100 days, and planets that are Earth-sized up to Jupiter-sized. So a number of these planets, number of these systems actually have more than one planet, and we could tell that because there were multiple transits where that transit signature looked different. So this is an example of all of these systems with more than one planet within them. Okay, so in those movies, the size of the circles indicate the sizes of the planets. So a number of the planets discovered were actually in systems with 2 stars. So they were orbiting not 1, but 2 stars, and we call these planets circumbinary planets. And so to date, we found about 23 and counting. Here is the list of these star systems where you have a planet orbiting 2 stars. I just want to mention one particular very interesting one. This is Kepler 47. This has a circumbinary planet. So its 2 planets are gas giants. One is maybe more like Neptune, and the other one is much larger, closer to Jupiter. And they orbit a binary pair of low mass stars, which are very close together. So for comparison, this is to scale relatively the size of our solar system. So these 2 binary stars are very, very close, with much within the orbit of Mercury. And this first gas giant is about the radius of Mercury. Yes, Wenping.
好，这边当然也延续，就是说，如果形成双星是要解决角动量的问题的话，那形成行星也是一种方法嘛。那伴星跟行星只在差于说，本身它可不可以点燃核子反应变成行星了啊？所以现在讲到的这个东西就是这几张投影片讲的，就是在双星系统里面可不可以有行星？因为发现行星已经不特殊了，现在将近有发现了太阳系以外发现了将近5000个系外行星了，所以现在在针对在于说，如果是一个双星系统，它彼此互绕引力啊就非常不稳定啊，那在这样的系统里面要形成的行星会怎么样的情形？他刚刚说目前利用这种零星的方式啊，就已经发现了好多好多，然后其中有23颗系统呢，它就是这种双星的行星系统。Thank you.
All right, thank you. So like our solar system, in Kepler 47, the planets are in a plane, just like our planets, and they have roughly circular orbits, just like our planets. They also are within the zone where liquid water can exist. And liquid water is crucial, we think, for forming life. So in our solar system, we are lucky. We're here on Earth within this zone, which is probably the reason why we are here today, listening to this talk, living these lives. In the Kepler 47 system, there is this planet in this special zone, but because it's a gas giant, we don't think it could actually be habitable and have life. Wenping?
好，这边一下丢了一些观念，就是离恒星的远近就决定了水有没有办法成液态的适当的温度，所以中间有一个字叫做 habitable zone， 就是适居区了，就是适合生命发展的区域。那现在当然对于系外行星来讲，我们很想知道有哪些行星是位于在这些区域里面。在这张投影片里面的那个 Kepler 47啊，就是科普勒太空望远镜观测的恒星的名字。那在天文上的习惯，大写的 A 就是主要的星球，质量比较大；大写的 B 就是它的另外一个伴星，那或者是 C 啊 D。那小写呢就是行星，所以Kepler 47小写的 B 就是第一颗系外行星绕着这个星球的 ，C 呢就是第二颗。那现在系外行星已经发现了好多个，它们其实可以到8个 一颗恒星或两个恒星周围有绕了8颗行星啊，所以是非常正在活跃的一个领域，就是研究系外行星。那这边讲的就是只是局限在环绕双星系统的行星。Thank you.
Great, thank you. All right, so what we know about planet formation, we know that the environment in the young system determines the properties of those planets. So the properties of the star in particular are very important. How bright that star is and whether it might have a companion, how much mass is in that disk around that star. All of these things will help determine the outcome of the system and whether or not there are planets and what their properties are. So this is an artist's image of a protoplanetary disk, a disk that forms planets. And you can see there are some rocky things forming here. It's still mostly gas, but you're beginning to get rings or gaps where young planets are carving out material from the disk as they orbit their star and accrete mass. So here's an artist's impression of what a young quadruple system might look like with a circumbinary planet. Here, these two stars have their ring of gas and dust, and within this ring is likely a giant planet which has carved out this material and is orbiting the star. So we think systems like this could exist and could have planets if they are in the correct or favorable configuration. That is, the stars are close together and there's a lot of dust and gas around in the disk. So in the past 10 years, we've also made a lot of progress in observing these young disks. In particular, ALMA, interferometers like ALMA, have allowed us to map out these disks and look at their sizes and how much mass is within them. So astronomers use the concept of dust to mean metal-rich material within that is usually concentrated into small molecules and then into micron-sized grains. So it's not quite like the dust bunnies, the dust in your house, but some of this dust is in the form of polycyclic aromatic hydrocarbons, which is what comes out of car exhaust. So this is a plot showing the distribution of masses in disks. And so it is increasing amount of dust, which is what the planets need to form to the right. So it's broken up into 3 different distributions. The masses of disks around single stars in blue, the masses in disks around binary stars, where the binary is more than 140 AU away, and the mass in disks around a binary star that are closer than 140 AU. So you can see these distributions are different, which tells us that the disks around these type of systems and likely the planets that form in them are also different. So we see that single stars have the most amount of dust in their disk or gas in their disk. And this is probably more favorable for planet formation because the more gas and dust is in the disk, the more likely we can get large planets and even multi-planet systems like our own. In contrast, when you have 2 stars that are close together, that are within 140 AU, those disks are the smallest, which suggests that circumbinary planets might be rarer than planets around single stars. In the case where the binaries are more than 140 AU away, it almost acts a bit like 2 single systems where each of those stars can have their own disk and each of the stars can have planets orbiting them. And so that's the green, it falls in the middle. So despite the last decade of observations, we still have a number of really basic open questions. So questions like, what is the fraction of multiple systems that form from each of these different mechanisms? We've captured them happening in nature, but we don't know how common each of them is. We also would like to know how these properties change with time. You could see from the simulations that these young stars interact with each other and their separations change over time. So we'd like to understand that better. And we don't really know how planet formation is different in these multiple systems. We're just now getting data of what these disks might look like and hints about what the planet properties might be like in these systems when they're young. So simulations help us to fill in the gaps of our knowledge. When we can't observe something in space, we can observe it on our computer. I'm part of the StarForge collaboration. This is a movie of a forming of a cluster of stars forming within a giant molecular cloud. So you're looking at gas density, and the brightness is related to how dense that gas is. You'll begin to see some white, very light dots appearing. These are where the dense cores are, which are forming these individual star systems. So now there's a couple of dense cores in the middle. You see a lot of complex filamentary structure within the simulations. As time goes on, you'll eventually start to see signatures of these young systems forming, where they launch very energetic jets of material. Like our own sun, they also drive winds that push out the gas. And so as these stars are forming within the cluster, they interact with one another. So those bright elongated things, those are the jets, and they show you where these young stars are forming. You can see that the stars are also very clustered. So they're much closer together than we are right now from our near neighbors, because at early times, they're much, much closer and only move apart with time. You could see some bubbles that were forming as a result of the winds. And the gas is getting messier and messier and hotter. You can see that with the orange and yellow. This is very hot gas. And so over time, these interaction of the stars with their environment clears out the gas and dust. So simulations like this one can tell us the distribution for how these multiple star systems form and how the number of siblings might change over time. They can also tell us about these young disks within these systems and how they might be different in multiple star systems versus single systems. And this will then tell us what is the time in which planets might be forming and what things might influence the formation of planets in these systems. So there's a very nice star cluster that's forming in the middle. The simulation forms a few thousand stars. The gas from this cloud is beginning to be cleared. And at some point, there'll be a supernova that goes off. So one of the massive stars dies and explodes, and the whole thing will turn green. There it goes. Okay. So this whole calculation spans something like 10 million years, which is about the time we think it takes to form a cluster of these stars. So this brings me to my conclusion. Our sun is lonely, and it's a little unique. Most stars like it do have a stellar sibling. We think that most of these siblings probably form from either disk or core fragmentation, and we now have evidence of this happening in nature with our recent ALMA observations. We have observed a number of multiple star systems that have orbiting planets. Some of the planets might be similar to our own, and some of them, like in Kepler-47, might be very different. The discoveries of star and planet formation are ongoing, and there's a lot of new and exciting results that we're continuing to publish and analyze as we get more data from these telescopes. So thank you for your attention, and I'm happy to take questions.
All right, thank you very much. So you're open for questions. Wonderful. This is the second time I saw that simulation. It's just amazing, incredible, and certainly would help to address a few more than just one question. Very good. All right, I pop my own 3 questions, but the audience is welcome to contribute. So the first question is it because massive stars have massive disks, which then favors a disk fragmentation, and that would produces equal mass binary, right? As we know, most O stars, B stars have equal mass companion. Is that the reason?
Yes, I think that that's the reason, because these disks are very massive, and so it's much easier for gravitational instability to happen. And then what happens is once you have this second star, it steals mass from the first one in that it's able to accrete from this disk. So there's a lot of material there. And this can also help drive it towards a more equal mass ratio. And of course, if they're very, very close, then they're literally transferring mass between them.
好，我刚刚问的问题是说，因为观测上知道大质量的 OB 恒星呢，多半都是双星，而且它的伴星呢，跟它的质量都差不多，这观测上是一个事实。那从刚才的演讲里面，我们知道说，这可能来自于原来形成这个恒星的盘子本身的重力不稳啊，所以就造成了这样的结果。My second question you didn't talked about is just how about observational evidence to distinguish different formation mechanisms?
Yeah, so right now it is a bit difficult to distinguish. So we, at these very earliest of times where we can see the disk, for example, and see that it's unstable, then we know that that's probably disk fragmentation. If we see the structure of the core and we look at the dynamics of the core, then that tells us it's core fragmentation. But once there's any evolution where, they'll say, 500,000 years later, then it's very difficult for us to distinguish one from the other.
Right, but at least early on for core fragmentation, the separation cannot be too large, right? And also for capture, then it's really a random game. So there will be a variety of mass ratio and maybe separation. I don't know. So 第二个问题我是问说有没有什么方法来辨别这些不同的形成的机制了啊。All right, my third question, if there's anyone, no, the circumbinary planet that you alluded to must not be stable, but the fact they are there. So is there any condition, for example, that the planet must be very far away from some close-in binaries, for example?
Yeah, so there is a condition if the planets are too close, they are unstable. So we want, in order to have a long-term stable system, we want a hierarchical arrangement, meaning we need the two stars to be very close together and the planet to be rather far away. And so these two stars are close enough that they act like one star, which makes it more stable. Now it's possible that a system like Kepler-47 had other planets that were closer early on, but they were kicked out because they were unstable. And so the ones that we see now are only the ones that are left on these stable orbits that are far away from the two binary stars.
第三个问题我是问说，那个环双星的行星一定是动力不稳定嘛？因为有两个星在那边，所以答案就是一定这两颗星要很近啊，相对于行星的距离。我问这个问题是因为我前几天就跟中一中在上课的时候啊，就是有中一中的学生问到这个问题，所以这就是回答到了。好，谢谢。My continue question. How about in binaries, but the planet is very close to one of the stars? Is there such a system?
Yes, you can have circumstellar. You can have the binaries be just around one of the stars,
right,
rather than both. And
that's also unstable unless the companion is far away, right? So,
exactly. Yeah.
So there are such systems.
I see some more questions in the chat.
Yes. Okay. So could you can read the question, right?
Okay. Well, I can read the first one.
Yeah.
So
how
many how many computer nodes is the simulation run on? So usually the simulations run on hundreds of cores, and we're running on a supercomputer in Texas where there's about 48 processors per node. So we're running on maybe 10 or 20 nodes, something like that. The calculations can scale up to hundreds of nodes, but you know that the calculations begin to be less efficient. So there's a trade-off on how much we can scale it to how many nodes, but that's a rough estimate there.
All right, thank you. The latest question is, you show the simulation and comparison with observation. The question is the initial condition. How to pick the initial condition, or theorists just simulate a lot of different models and then pick the one that fits the observations best?
Yeah, that's a great question. So what we do is we we study these molecular clouds and we study their properties. And so when we set up a simulation, we try to set it up with conditions that are like these molecular clouds that we've observed. For example, the same masses, sizes, velocity properties. And so that gives us some initial reasonable condition to start from. But the problem that we always have is that these clouds are connected to the larger galactic environment. And so at some level, we have to start with a little bit of artificial condition. So the simulation you saw started as a sphere, which most of these clouds are not spheres. But by simulating a large cloud with the properties like the ones we observe, we can get the small scale processes more accurately than if we're just trying to start on a small scale with these conditions.
All right. 不晓得这个 Andrew 有没有听到，就是有些当然就可以用观测到的分子云里面的环境嘛，就直接开始，那是最原始的诞生恒星的环境。那有些当然因为做模拟，它就得把它理想化一点，比如说这个云气是球形啊等等这些事情。All right, the next question, Stella.
I see someone has their hand up.
All right, so there's a question now.
Okay, so can you hear me? It's okay, Professor?
Yes.
Okay. So good morning, Professor. So my question is, as you say, so we know many OB star, they has high massive, and maybe this is a double star, but they still has planet in here. So my question is, in theory, we know when the two massive stars that spin each other, they will be produce gravitational wave, and their magnitude too are very complex. So how the planet, their orbit can keep the stable and successful to survive in this kind of system inside. So this is my question. Thank you.
Yeah, so it is really interesting to think about planets or what planets might be like around high mass binaries. I think we think that these planets might be very rare in the sense that the time it takes to form these planets is maybe a few million years for them to form and settle into their configuration. And the lifetimes of massive stars are not that much longer than that. So I think there's an added challenge there where you not only have to, form them in stable orbits, which is harder because the stars are more massive and they're more likely to be binaries, but the timescales are so close that these planets may not have it may be very difficult to actually form planets from the disk just because of the environment and the relatively short lifetimes of the really massive stars. So I don't think we know of any planets around massive binaries at this point. Mm-hmm. They'd be very hard to find just because of the contrast between the star and the planet. But that, we might be able to use other ways, other signatures to find them, but it will be pretty hard.
Okay, thank you, Professor.
Great. So the next question is on the message board. It's about retrograde motion.
Yes. Can we produce a protoplanetary disk with a retrograde direction, meaning that can we produce a disk where the gas is orbiting and the planets are orbiting opposite the direction that the stars orbit?
Right.
So we are always looking for these. We see a lot of examples of misaligned disks where the orbits of the stars are this way and then the disk is that way. I wouldn't say a lot of examples, but we have some examples of that where there's some misalignment. I don't know of any examples where the disk is flat out retrograde compared to the stars. You can imagine that this might be possible if you have a very clustered environment with a lot of interactions between stars, that maybe through capture, we collect a star and its angular momentum is the other way. We are actually looking for these kinds of things in simulations. So maybe we'll have a better answer in a year or two once we finish our star forge calculations. But yeah, that's something we don't actually know of one yet, to my knowledge.
这个问题是说有没有，就是因为有些行星系统它行星公转的方向跟恒星自转的方向相反或不一致，那现在都还不太知道这样的问题。那这个是比较复杂的问题了，因为中间还可以有碰撞还是整个行星系统都是这样子。很好，我没有把所有的问题都用中文解释，我想是因为是录影，录影有很大的好处就是大家还是可以重复的看那看多了大概也许就可以知道一些事情了。All right. Can I follow that question with another one? So in star forming region, come back to binaries. Do most binaries have a preferred orbital plane inside the same cloud?
That's a great question. I think the answer is no. But what people have been trying to look at is to see if there's some preference on small scales. Mm-hmm. So, for example, if there's a filament, is the binary likely to be aligned with the filament direction or not? This is still a bit hard to do with observations because you have this narrow window between when there's gas and when there's disks. For us to observe that, but people have tried to do some models of that and are starting to do some kinds of studies. But I think on the global scale, there's likely not to be alignment, but maybe on smaller scales, there is some alignment, but we don't really know.
Mm-hmm. The idea, of course, that they could be influenced by magnetic field. So that's but they also evolve. All right. So 我刚刚一个问题就是问说，在同一个分子云里面很邻近的这些年轻恒星的双星，它的轨道面有没有一个规律性啊？答案就是说不容易研究了。不过好像目前看起来是没有，因为他们还有很多其他外在的影响。All right. That's so far has been very, very good. Any questions? I actually don't know how many of you are high school students. I hope some of them are from Taichung Yizhong. I hope. All right. All right. Any more?
It looks like there's another question from
All
Andrew.
Right. There's another one. I don't. Let's see. How come I don't?
I can't read it. So.
Oh, I'm sorry. Could you recommend some books or articles in the subject?
Oh, I'm so glad you asked that. If you're asking about reviews of stellar multiplicity, I just have written a review article that's coming out and posted to AstroPH, to our archive, on Monday. So if you want a fairly high-level comprehensive review of what we observe for binaries, that would be the thing to read. There are a few books on star formation generally. I don't know what your level of interest is. There aren't really that many at a basic science level. One particular one is Star Formation by Derek Ward Thompson. But that doesn't cover just the formation of multiples. Probably doesn't have a lot in there, but it does cover star formation in general and how that process happens.
All right. So Ward Thompson 有一本比较薄的书了，那就是有关于恒星形成的。那至于双星的话，这个Professor Offner 他刚刚出了一篇review 的文章，礼拜一星期一会上 AstroPH， 所以就请你下载吧。Wonderful. So you planned that question, right?
Yeah, I must have.
All right. Great. All right. This has been fun. It's 欧教授那边已经很晚了，已经晚上10点多了，所以我们很感谢他。晚上的时间呢，他还有个小孩子呢，那来帮我们给了一场非常非常精彩的演讲，有关于双星，以及到后来有关于系外行星两者之间的关系。So thank you very much, Stella. So we appreciate your effort, and we look forward to seeing you sometime soon in Taiwan.
Yes, I hope so. Thank you very much, and it's been a pleasure.
All right. Thank you. Bye bye. 谢谢大家咯。